Our third integration technique is called partial fraction decomposition. So to start with, what I want to recall is the process of finding a common denominator to combine rational expressions. So if I were to start with 2x plus 1, and I add to that minus 3 over x plus 2. What we typically do is get the common denominator, which is the product of the individual denominators. And then think about, in some sense, cross-multiplying. So we would get 2 times the quantity x plus 2 minus 3 times x plus 1. Now, we could simplify this a little. The denominator here can be expressed as x squared plus x plus 2, so plus 3x plus 2. And the numerator, I have 2x and I have minus 3x. I have 4 and I have minus 3, so that becomes 1 minus x. So the technique we want to look at today actually does the reverse. So the significance here is, imagine that you were asked to integrate something that looked like what we have on the right. That's very complicated. If I can decompose that into the two pieces on the left, those are much simpler to integrate. So that's going to be our strategy. So to illustrate this, like I said, suppose you start with the integral on the right. So we want to evaluate 1 minus x over x squared plus 3x plus 2, the integral of that. Now, of course, right now I can see how to decompose that. I know exactly what we started with. But what if we didn't have that? How are we going to be able to find those requisite pieces on the left-hand side? What we first do is, our goal is to recognize that the denominator can be factored into what we call distinct linear factors. I will say, if you look in the textbook for this section, there's actually, this topic is much broader than what we're covering on our syllabus. So we will only look at this when like I said, the denominator can be factored into linear factors, so x to the power 1, and what we call non-repeating, so not having like x plus 1 times x plus 1. Those are covered in the textbook, but you'll notice that none of those problems have been assigned. So I would identify that it could be factored, and then what I start with is I take my integrand with the knowledge of how it factors in the denominator, and I'm trying to express it as a over x plus 1 plus b over x plus 2. And we want to figure out the value of those constants a and b. So one thing that can make this simpler is if I multiply both sides by that common denominator on the left, this yields 1 minus x equals, so when I multiply that common denominator by the first term, the x plus 1s will cancel, and that will leave me with a times the quantity x plus 2. And similarly, this becomes b times the quantity x plus 1. And we're saying that this needs to hold for all x. What we can do to solve this is be strategic and plugging in certain values of x that will simplify this. And in that case, it's really the roots of the factors. So notice that if I take that expression and I, for instance, drop in x equals minus 1, on the left-hand side, we get 1 minus a negative 1 is equal to a times minus 1 plus 2 plus b times 0. So the significance of plugging in a root there is it removes one of the unknowns from this expression. So we're going to get here that 2, the left-hand side, is equal to a. So now we found the constant a. If I plug in the other root, in this instance, minus 2, on the left-hand side I get 1 minus a negative 2 equals a times 0. So effectively removing, even though we know a is 2, this is removing that from consideration, plus b times minus 2 plus 1. So this gives us 3 on the left side equals minus b. So consequently, b is equal to negative 3. I use that information to now go back and drop those in for my constants here. And so I'm going to know that the integral that I started with is equivalent to integrating the decomposition here, 2 over x plus 1 plus negative 3 over x plus 2. And one thing, and often I'll in examples kind of skip to this next step, this is the same thing as twice the integral of 1 over x plus 1 minus 3 times the integral of 1 over x plus 2. And so finally, I want to evaluate these integrals. I'll point out that technically you could do a u substitution on these integrals where you let u equal the denominator. It turns out because we are always looking at linear factors, we would end up with a natural log function. Importantly, if we had a quadratic, that wouldn't necessarily be the case by any means. Consider 1 over 1 plus x squared, which the integral of that yields arctangent. But we're always going to have linear factors. So if it's unclear, do feel free to really write down that u substitution, but you wouldn't have to show it in your work if it is clear that I am going to get twice the natural log of the absolute value of x plus 1 minus 3 times the natural log of the absolute value of x plus 2. Again, it's indefinite here, and I can add my constant c here. Unlike the previous two techniques, I think the bounds having definite integrals is more straightforward here. Whatever the bounds are on the original integral, you would use the same bounds on your pieces that you have kind of decomposed this into. And I'll point out that it's perfectly fine to write this in this way, the final answer here, but you might find that in checking your answers for the textbook, a lot of times they use log properties to simplify this. So keeping in mind that that is a possibility and being able to cross-reference there to see if it's equivalent to the answer you've written down.